Hello everyone. Finally, we returned back to physics. We're gonna take lesson 1 in physics, light and quantized energy. Here we have a wave, and the distance from this point to this point is the wavelength. The length of the wave, this wave, this from this point to this point is the length, so we name it the wavelength, and we represent wavelength as the symbol lambda, and crest here. Crest is the highest top in the wavelength, and the trough is the lower part in the wavelength in the wave. So here we have a wavelength, and here a wavelength. And amplitude is this going increasing wavelength and decreasing wavelength, increasing wavelength and decreasing wavelength. This is called the amplitude. So, well, though, so yes, wavelength is usually expressed in meters, centimeters, or nanometers. So 1 nanometers equal to 1 times 10 raised to the negative 9 meters. So here, a particular frequency can be expressed in the following ways. 652 hertz equals to 652 waves per second. Hertz, we use it when we calculate the frequency, is the same as wave per second, equals to 652 per second equals to 652 s negative 1. S negative 1 is the same as here, 652 meters per second. Electromagnetic wave relationship. There's a formula which is C equals lambda times V, which is frequency, or you can say F instead of V. Now lambda represents for the wavelength. Here, C is the speed of light in a vacuum, and lambda is the wavelength, and V is the frequency, as I said now. So, example, find the frequency of a light having a wavelength of 7.52 multiplied by 10 raised to the negative 9 meters. So here we have a relation between frequency and wavelength. So we use the formula C equals lambda times frequency. Now the speed of light in vacuum, here we don't know it, but you need to memorize this number. C is 3 multiplied by 10 raised to the 8th power equals lambda. The wavelength is 7.52 times 10 raised to the negative 9th meters times V. So we divide both sides by 7.52 times 10 power minus 9, and here we divide it, so we get V equals about 3.989 times 10 power raised to the 16 hertz. Here's another example. Calculate the frequency of a yellow light with a wavelength of 58 times 10 raised to the negative 9th power. if we have a relation between frequency in light and a wavelength, we use the formula C equals wavelength times frequency or V, it doesn't matter. So we know that the C is the speed of light in a vacuum, so C is 3 times 10 raised to the 8 equals the wavelength is given 58 times 10 raised to the negative 9 times F. So we divide on both sides by 58 times 10 raised to the negative 9. So finally we get F equals to 5.172 times 10 raised to 14. Now the calculator, it will give you a long decimal, but actually when you use calculators and you are calculating big powers, you choose the three numbers after the point. If you have a decimal, for example, 5.92384. I'm giving you an example. We take three numbers after the decimal, which is 9, 2, and 3. We put 5 and we put the point and we put 9, 2, 3. We choose three numbers after the decimal. Here actually I forgot to put the unit. The unit is hertz because we are finding the frequency. The frequency is in hertz. Relation between energy and frequency. The formula is E equals H times V, where E represents for energy, H is Planck's constant. Now we're going to talk about it. V represents for the frequency. Now what is Planck's constant? Planck's constant H has a value of 6.626 multiplied by 10 raised to the negative 34th power joules, where G is the symbol for joule, the energy, SI unit for energy. Here Planck's constant, which is about 626 times 10 raised to the negative 34th power. Example, find the energy of a light with a frequency of 340 times 10 to the 15. Here we have a relation between energy and frequency, so we use the formula E equals HV, where E is the Planck's constant. So Planck's constant is about 6.626 times 10 to the negative 34 times V, which is the frequency. We have the frequency 340 times 10 to the 15. So we multiplied them and we get the answer 2.252 times 10 to the negative 16 joules. We put three numbers after the decimal. Second example, calculate the frequency of a light with an energy of 2.5 joules. We apply the formula E equals H times F or V, doesn't matter. So E is 2.5 equals the H, which is the Planck's constant number 6.626 times 10 to the negative 34 times frequency, because the question is calculate the f frequency. So we get f equals 3.773 times 10 power 33 hertz. The last part in the lesson. Example, here we have a Bohr model and we have four levels. Level 1 here, level 2 and the second level, and here is level 3, and here is level 4. So the question, find the energy absorbed by an electron that is existed from energy level of 2.5 joules to energy level of 5.9 joules. So if we are finding energies, we apply the formula E, which is equal to E2 minus E1, and E2, which is the final energy. Final energy here is 5.9 joules minus 2.5. 2.5 is the starting joules, so which is 3.4 joules. We open parentheses and say gained, because the energy here is positive, which is 3.4 joules positive. If it's negative, we say lost joules, because here we are asking about energy. The last relation between energy and wavelength. There's a formula that tells about energy and wavelength, which is E equals hc divided by wavelength, where E is the energy and h is the Planck's constant, and c is the speed of light in vacuum, divided by wavelength. So, example, find the energy of a light with a wavelength of 470 times 10 to the negative 6 meters. E equals hc divided by wavelength equals 6.626 times 10 to the power of minus 34 times 3 times 10 power 8 divided by 470 times 10 to the negative 6. H is the Planck's constant, which is this value, and 6.626 times 10 power minus 34 times the speed of light in vacuum, c, which is 3 times 10 power 8, and the wavelength is given 470 times 10 to the negative 6. Apply this in the calculator and it will give you 4.229 times 10 power negative 22.